Reverse engineering is the process of taking an engineered artifact like a software program, a coffee pot, or a car, and figuring out how it works at a deeper level. Sometimes we reverse engineer something to build features on top of it. Other times, we're interested in understanding its security properties. While reverse engineering information technology systems like cell phones and computers is a well-known field, reverse engineering operational technology is relatively less well-known. In this episode, special guests Robert Peaselee and Brian McCord discuss this exciting frontier of technology, hacking, and cybersecurity. Brian, Rob, welcome to the show.
Thank you, Josh.
Thank you.
Robert Peaselee has over a decade of experience in offensive cyber, supporting multiple clients across the Department of Defense and providing tools to red teams at Fortune 500 companies. He has attacked everything from servers to cell phones and engine control modules to armed personnel carriers. He is currently a senior reverse engineer at Shift5. Brian McCord has a background developing cyber capabilities and planning offensive cyber operations for the US military and beyond. He has over 7 years of experience leading engineering teams charged with solving complex cybersecurity research problems and helps bring the hacker mindset to bear on work at Shift5. He is currently vice president of labs at Shift5 and responsible for all vulnerability research and reverse engineering at the company. Gentlemen, welcome to the show. So this is a really interesting topic for a lot of folks that are in and around technology, maybe people that have been in information technology administration or software engineering. And they've always wondered, like, well, what do these reverse engineers do? And how do cybersecurity professionals take a look at software that they don't have the source code to? And furthermore, how do they do this on things that aren't even software or some combination of hardware and software? So I wanted to spend a little time with you guys today talking first off about what reverse engineering is, and then get into some of the tools and techniques and really what is a day in the life of what a reverse engineer does. So maybe we can start off with just defining reverse engineering. What is it, and maybe go from there.
Sure, I can take a crack at it. So what reverse engineering really is using all the tools at your disposal to understand something that you don't really have good documentation or a good sense of what's going on, right? So for example, if you're living in the IT space and you're a computer coder, most of the time you're given the source code for something, right? It's got the Python, it's got the C code. You can go line by line and figure out exactly what's going on inside your piece of code or inside your hardware device or on your microcontroller. You can see the scripts that are running, the code's running. Well, what happens if you can't do that, right? What happens if no one gave you the source code, or the manual for what you have doesn't exist, or you don't have the deep down technical manual for the car that you're trying to look at? How do you figure out what's actually going on inside the black box? And I think, throughout the rest of this podcast today, we're going to go through some of those techniques. But the idea is, if I'm given something and I have no idea what's going on inside, what sort of code can I use? What sort of physical processes? What sort of understanding about how these sort of hardware and software components normally work can I use to backtrack, learn small bits of pieces about that black box, and then start to put it together like a puzzle where one piece unlocks what another piece is doing, which unlocks more, until eventually you have a complete understanding of what is going on inside that piece of software or that hardware. And now you can understand it and manipulate it to do other things.
Gotcha. So, Robert, when we think about a piece of software that's on your laptop, to a layperson, you might think, okay, well, the software is on the laptop. Why can't you just go look at the software and understand how it's written? A human being wrote the software. You have the software on your computer. Just go read the software. Why do you have to go through this process of reverse engineering?
The process of building software, going from source code, it goes into like this funnel, and in goes source code and out goes machine code. And that machine code cannot actually be easily translated back into source code. So we have a lot of tools that will help us take what is just a bunch of ones and zeros and convert that back into what we call disassembly. And the disassembly is very close to what the processor actually sees and executes those instructions. Luckily for us, as time has gone on, the tools have gotten a lot better too. So we can actually get back to what we consider a pseudo code. It looks kind of like source code, but isn't. And there's still a lot of work that has to be done to understand things like the data structures and the program layout and how it all executes in memory and all that.
Gotcha. So the way software is written, there's almost like a forward engineering step of like you've got source code, something that certain human beings can read. And that gets translated through something like a compiler,
Mhm.
makes machine code that the machine knows how to run, the ones and zeros. And it's not a straightforward process to go from the zeros and ones back into source code, right?
Exactly right.
Yeah, so it sounds like kind of a giant pain to take these binaries, right? This machine code and turn it back into something that people can understand. Besides just a morbid curiosity in how these things work, why would somebody go through the process of reverse engineering something?
So it's actually an interesting question. And that's what I was thinking about while Brian was describing, like, why would someone go through all that pain? I started off as a malware reverse engineer. So you initially get a sample in, it's a binary. And how do you know if it's doing exactly what the source that you got it from is saying that's going to do? So how do you know that, your version of a PDF reader on your computer is just reading PDFs? How do you know it's not taking a copy of that PDF and then sending it out to someone else that you don't really want reading what you're viewing on your PDF reader? Well, that's what initially reverse engineering for me, that was my entry point, is just doing that verification and making sure that a binary was not malicious. But over time, as my skill set developed and my aspirations changed, you start to look at software, and if it has a bug in it, if it's taking some sort of input and then it's not handling that input properly, can you make the program do something different than what it was intended to do by the original author? And that's when we start to get into the vulnerability analysis and exploitation. And I would say that for many cyber professionals, the pipeline is pretty similar. You start off either in malware analysis or developing cheats for games is another huge area that people get their start in this. And then you start to go where, your interests take you now that you have the ability to analyze a program to see if it's doing exactly what it's supposed to be doing.
Yeah, that's so interesting. I've seen this time and time again that people who are into video games start poking around and kicking the tires and saying like, I wonder if there's a way that we could build a bot, or if there's undocumented features in this game that we can exploit. Tell me a little bit about what that looks like. I mean, have you done any game hacking before, or know people that have done it?
Yeah, I'm going to get crucified for this. So, there's a natural interest. Like, how do you take a system like a game engine? And for me, it was seeing stuff that other people had released and like, well, how do you make it so that you can see through walls? How do you make it so you can make it so your guns always point at an enemy's head in a first person shooter? And so I got my teeth cut on like enemy territory, the Wolfenstein mod.
Perfect.
And I would say that even now, it's like still a huge, like almost training ground for people, because enemy territory went open source, and now it's a lot easier to see, how do you hook into this process that's running and then find like all these procedures and then like inject your own code in them to make do different things. And it's become like, I would say almost like the game hacking training ground now. But that's exactly how I got my start.
Right. Yeah, it makes a ton of sense because there's an analogy there that's so close to developing malware, right? So when you're building a game hack, you've got, forward engineered software. You've got binaries without source most of the time that are on your computer because, you're running the game, and you want to build programs that lay on top of that and provide additional features, which maybe the game designers don't want you to have, but nonetheless, it's your computer, right? So you can bump the bits around how you want. And that's not super dissimilar from how a lot of malware authors are trying to do things, right? There's a service that's running on some computer somewhere, and it's well-known software that's running on it. And you've looked at that software and realized, oh, there are some undocumented features in here that allow me to run code in a way that no one anticipated. So you build a payload that, puts some unanticipated input into this service and get it running on that other computer. So I think there's just like the mentality of like, I get it. You've got rules to this system. I want to do this thing and you're not going to tell me not to. And so I'm going to figure out a way to make it happen. Is like, that mentality and that skill set seems to be pretty common, right?
Absolutely.
And I think there's also another interesting class of usages that this conversation around game hacking opens up, which is, sure, it is very clear that cybersecurity is a huge component of why people reverse engineer stuff, why you write systems programs and low-level programs to like lay on top of these finished binaries to do the things that you want to do. But there's also a whole interesting class of just like hardware hacking and modding things, right? You've got this finished product, but maybe you want to add some custom features to it, right? I remember back in the day when I first got my license, like I put a computer in my car and like
Me
had a
too.
little LCD screen. Yeah, right. You know, and like you plug into the OBD2 port and you get like diagnostic codes and you can see like I mean, it's kind of stupid that you have a tachometer in your dash, but how cool is it that you can put it on an LCD screen? You know, you can start modding things in ways that the manufacturer maybe never thought of. And that's reverse engineering, right? Because you've got a finished product. You're figuring out how it works through like thinly or totally undocumented means, and then you're adding features on top. So there's a part of reverse engineering that's also adding features to finished products, which comes in handy in a whole bunch of contexts.
And one that's I've actually been seeing a lot of lately is you get a cheap webcam that's made in China and you bring it over, and you don't want there's two avenues, right? Like first, maybe you want to make sure that firmware it comes on that camera is only allowing you to view it locally. But another big one is a lot of the service providers are going to like a cloud model. So you buy the camera pretty cheap and you have to pay a subscription fee to, actually store and view your feeds. And people have been developing through reverse engineering alternate firmwares that allow you to like view your streams locally. And I think that's completely like enabling the consumer to take a piece of hardware and use it the way that they want to, because it's theirs.
Yeah, I think it's so like liberating when you've got the ability to take a piece of hardware, something that you've bought, and you can customize it to your purposes. I know there was like actually a big legal fight with some of the farm equipment manufacturers, right? Like they call it like I think the right to repair or something like that is the name of the movement. But it's essentially this idea that like, hey, I bought this tractor, and it's important for my livelihood. I should be able to repair it and mod it and do things to it as I see fit. And there's like some really interesting legal challenges around this concept. But it all comes back to reverse engineering, right? The ability to take something that's a finished product, understand how it works, and then layer features on top of it, right?
Goes back to the the use case you were talking about before. So in IT space, a lot of it has to do with how do I add a feature to software. In OT space, where a lot of this reverse engineering gets started, is these practical effects, right? So for example, in the car community, let's say your dashboard light goes off in your car and something's wrong. It says check engine. Well, back in the day, you used to be able to pop the hood, figure out exactly what's going on because it's all mechanical, right? Something is snapped off, something is broken. But nowadays, a lot of these error codes are generated by the computer on the vehicle in an embedded system. They're stored in the memory on the computer, and you have to access them through the OBD2 port, which normally the car mechanic is the one that has to do. But let's say you don't want to spend a few $100s on labor hours for the mechanic to go in, plug in his special cable, and get all the data off for you. How do you figure out what's wrong with your car, right? So there's been a lot of like kind of car modding communities that turn into like car fixing communities by trying to reverse out, okay, I can buy equipment like a $30 Raspberry Pi, put a $20 can hat on top of it, and watch the bits transit the line. And I can notice things like, oh, it keeps sending this message that starts with like 0B in hex, and then there's 40 bits of data, then there's some ending bits, and then it keeps sending that over and over. So what is that? Then they can start doing like the Googling, right? Like, hey, are there any charts or manuals or a mechanic somewhere who's got a manual who wants to scan it, put it on the internet? And then they start to break down this knowledge from essentially a zero knowledge game. All they know is there's a computer on the car and something's wrong. And start to look at the emanations from the box, look at the data transiting the critical lines. And then they turn that into a fix for their car, right? They see, oh, I see that my catalytic converter is messed up. So I'll just go replace that. And I'll save myself $400 for the mechanic to go plug in and find that out. And same thing with tractors. People were trying to fix their own tractors when the company was saying, in order for us to tell you what's wrong and fix it, you need to bring it into the warehouse. We need to deal with
an authorized dealer. Yeah.
Authorized dealer. And so that costs people money, right? So there's oftentimes an economic incentive to this. And then, of course, we at Shift5 are most concerned about the cybersecurity interests. So if you can do things like read data off a vehicle and you can determine like, hey, this is the message that says your car's broke, what sort of malicious things can you do, right? Can you, let's say, reverse engineer what that protocol looks like and then create messages that do things like turn the car left or turn the car right or engage the anti-lock brakes. And, maybe it's a system as small as a car, but maybe it's huge. Maybe it's a plane or a train or a tank. And that's where we really start to get traction in our reverse engineering fields. It's like, let's figure out what kinds of things a malicious actor could do to these major end item systems. That is as simple as finding the right kind of message to send if they just have the time to sit there and kind of break apart the puzzle pieces to figure it out.
Totally. There's so much to unpack there. I think like one thing that might be helpful would be just to center on what that you said OT, kind of digging into what OT is, operational technology. I mean, the way I think about these things is information technology, things like cell phones, laptops, network gear. They're there fundamentally to like manipulate information and data. And people use these to make decisions that, business decisions. That's really what IT is all about. But OT, operational technology, things that sense things in the physical world or actuate levers and motors and things, things like robots and locomotives and aircraft. These are things that are there to do business operations. And there's like a really important distinction because they're just the technology is used for very different things. But to your point, OT has like just seen an influx of digital components into these things, right? Now, what's interesting is most of these components, most of the time, aren't running Windows 10. And so from a reverse engineer's perspective, there's really, it's a very different environment. And one of the things I wanted to dig into and something you have deep experience with, Robert, is let's talk a little bit about what reverse engineering looks like on an IT side, typical things that a reverse engineer would do to reverse engineer a game binary or a system software, something that's in the Windows kernel, versus say when we're looking at a car or a locomotive or a military weapon system.
I'd say the biggest difference is that the tooling is so much better on the IT side. So whether you're looking at a phone, which has like emulators that you can run on, or at the very least there are ARM processors, and you can do things like load up engines that can run or emulate either pieces of code or full applications, whatever. It just exists. And the same thing on like the Windows and Linux side. If you're looking at a binary that runs on one of those systems, you can just run it inside a virtual machine, inside of a virtual environment, and you can almost always replicate the state of the program that you're looking at and do things like dynamic analysis, which means that we have tools, all debug, Canvas, and Immunity, all these other things that we can just step through programs and actually analyze how they're running. On the OT side, just getting the firmware can be very difficult and require a lot more steps up front to get to the part that we can actually feed into some of the tools. And then the tooling is worse. And that's because, they're using a lot of microcontrollers with less known architectures. So it's not, Intel x86 or x86-64 or ARM. It can be some microcontroller specific architecture for that one company that produces that microcontroller. So it's just the tooling is the biggest part. And then also getting access to the part that we can actually analyze with those tools is.
Yeah. And so maybe it sounds like some of the techniques are similar though, right? So you said static and dynamic analysis. So static analysis is, hey, we're going to take this binary or this program and we're going to lift it up into from the zeros and ones into a representation that at least some people can understand, disassembly, right? And then maybe use some tools that help us pull that apart and map out how the program flows and look at like if-then statements and different branches in the program tree. But you're fundamentally looking at something that is frozen. The program isn't running when you're doing that. You're just sort of reading through how the general flow of the program looks. Whereas when you do dynamic analysis, you're actually setting up an environment where you can watch the program in a sandbox and understand, okay, as I'm stepping through this program, seeing how data is getting manipulated in the IT side or in the OT side, actually seeing the whole system move in the physical world and sense data and things, right? So, but the tools you're saying are not nearly as good on the OT side. And one of the other challenges is just even like extracting firmware from these devices, right? So maybe we could talk a little bit about that problem, because on the IT side, when you think about a game binary or something. You've got an executable that's just sitting in a folder on your Windows box, and you can take that file, pull it into a disassembler, and go to town, right? Tell me a little bit about maybe some of the recent projects you had where you're looking at hardware, like there's a board and you're like, okay, this is my starting point. I need to get this into a disassembler. Like, what does that look like?
Oh man, there's so much. I'd say that the big difference, like just at the very most basic level, is when you have a program that runs on an operating system, it's got an interface to the operating system that talks, and it gives us a large surface that we can watch how that program works. So that's your IT side. And I actually also want to throw in IoT, so Internet of Things stuff. A lot of times when I see people talking about doing firmware analysis on the IoT side, it's usually like you find some sort of a JTAG or serial port or something that exists on the board that you can then interact with. It's usually running some version of Linux or some embedded version, like stripped down version of Linux. And then you still have the same thing where you have a ELF binary, which has a lot of these interfaces, and the tooling is actually not that bad. So right. IoT like kind of has that. You're still running an operating system.
It's running an operating system.
Exactly. When you get on the OT side, we're usually looking at an ECU, an electronic control unit, that has no operating system, right? So there's no interface other than like reading out of a register, finding some data, maybe like looking up and taking action on the data and reading it back out like to something else, like, and usually really quickly. And not having that operating system makes things much more difficult, because now we have to look at a lot of the times, what do you do when your hardware has no memory allocator or has no,
right.
No standard interfaces, no standard libraries that we can use to accelerate the reverse engineering process. That makes it a lot more difficult. And do you want me to talk about how we get to the point of being able to actually?
Yeah, sure.
Software? All right.
Yes, you've got these real-time systems like all over this board, and you want to pull it into some tool so that you can start getting a sense of what it looks like. How do you do that?
So there's a lot of digging initially. Initially, when I get a new piece of hardware, the first thing I'll do is you'll take it apart and look at it and try to get an idea of what the microcontrollers exist. Usually start looking at the big chips. The little ones you don't care about as much. The big chips are generally where the core of the processing happens. And then you start doing, those dives. You start looking for data sheets. You start looking for, those shady websites that have someone that's uploaded something that can help you to get an idea of the architecture, to get an idea of the memory layout, and to get an idea if any of the pins on that chip have some sort of debugging access, whether it's like serial wire interface or like I said, JTAG or whatever. And there's a lot of proprietary interfaces as well that you can then maybe like plug in your hooks onto, like I'm talking about hardware, physical hooks, and then start to see if you can interface with the chip that way.
And so microcontrollers are really interesting to people that maybe haven't touched hardware before. How are these different from just like regular integrated circuits that are on a board?
So microcontrollers generally have a processor. I'm not going to say general purpose processor. So your computer might have a general purpose processor, which is meant to take and execute arbitrary instructions. A microcontroller is not considered usually general purpose. It can execute a very, usually a limited set of instructions that may be specific to that microcontroller, that family of microcontrollers.
Gotcha. Yeah, but they're like closer to computers than just a series of logic gates like an integrated circuit is. So like you can compile software and upload it onto this thing while it's soldered to a board and like fundamentally change the way that the system operates, right?
That's correct.
And when you're hooking up those pins, you're almost like wiring into that process, literally wiring into that process where the programmer of that microcontroller was interacting with that thing when they were uploading the firmware, right? Like oftentimes these chips have like debug settings so that you can step through and do dynamic analysis on the chip and make sure that, I have this weird like thing that happens, like the robot arm goes crazy when, the full moon is out and it's, certain humidity or whatever. And you can emulate that condition and debug the chip. And a lot of reverse engineering is actually like repurposing debugging tools for the purposes of understanding what's going on, right? Because that's ultimately what they're supposed to be doing. So you've got these microcontrollers, you're pulling the firmware off of them. when you pull the firmware off and you're looking at the disassembly, you're getting a sense of how these programs are laid out. And that's the static analysis side of things. But sometimes you want to do dynamic analysis, right? You want to get this thing running in some sort of sandbox or some sort of conditions and see how the inputs and outputs work, right? Because oftentimes using dynamic analysis and static analysis together gives you a better understanding of the system than either of them in isolation. But when you're talking about an OT system, like building a sandbox can be a little harder than it is on an IT system, right? Because it's not just a DLL or an executable or an ELF that you're like running in an emulator. You sometimes have to build like workbenches, right? So I know, Brian, you've done this quite a few times, building these cyber integration labs.
Yeah, I mean, one of the big problems is that like in the IT world, you have these kind of known underpinning resources, right? Like, you know, you're going to run your software on top of an operating system. It's probably going to be either Windows or Linux or something else. And like Rob was mentioning, there's all these tools that can give you these virtualized environments, right? You can go download VirtualBox, you can get a VMware suite, and then you can open these things up, run them on something that's not really going to damage any of your equipment, and then play around with it. Big problems in the OT space is that everybody's microcontrollers are slightly different. Everybody uses slightly different ways of talking to things. Sometimes there's custom instruction sets that aren't, x86 or ARM compliant. And now you're in a problem, right? So you can kind of step through it in that one, you can start to just look at kind of almost like a web API, right? Like, you send certain things in, like if I charge this voltage or send this message over the CAN line, then I'm going to get this effect out, like the arm moves up, it moves down, moves left or right. And that can give you some basic idea about how the internals are working. But often what happens is like, you've got to do more than that, right? So you've got to pop the top off. You've got to literally try to pull the code off the chip, usually using like physically invasive means, right? And then what do you do when you have this firmware code? We've got to put it somewhere. Some people try things like QEMU is a great way to try to do some basic hardware emulation, but it's limited in what it can emulate and what it can do. So if you can't do that, then you're kind of stuck. So like virtualization is best, being able to emulate what is actually happening on the device without breaking anything. But oftentimes we just have to face the cold hard reality of like, there's way too many possible combinations of custom chips built by original manufacturers. And so you just end up having to say, look, I'm just going to buy 3. I'm going to play with one, use one as a reference, and one's my backup when I assuredly break the first one, trying to do stuff to it. And that's kind of the more realistic play on how people really look at reversing this stuff.
So one of the interesting things about what you just described, Brian, is there's a lot of just like very minute details when you're quote unquote playing with the with this thing to try to pull the firmware off or to figure out what the protocol looks like as this chip is communicating over a bus. Robert, what are some of the tools that you commonly use to try to achieve those goals of, like, say, doing packet collection on one of the serial lines or removing the firmware from a microcontroller?
So I was going to say, well, we don't have like an operating system, and we don't have like a something that we can reference for a normal way a binary executes. What we do have is a lot of standardized ways that these things communicate. So like you're talking about, you mentioned CAN, the controller area network is it's a data bus, and it's used widely across different components. So once you understand that a CAN bus looks a certain way over like an actual wire, then we can use things like oscilloscopes and logic analyzers and start to look for, while a system is powered, voltage patterns that match what we'd expect a bus data to look like as it transits these things. And there's several standards. So the first tool that I would say that you need to do this kind of work is expand your knowledge. You have to go beyond like understanding like TCP/IP as your protocol for analysis into CAN bus, into like the very many serial protocols that they have, and start to understand, the synchronous versus asynchronous and unidirectional or bidirectional over like one wire protocol, all that. And it helps you get a huge jump into what something is doing and why, and then start to bring in your other tools that are actually like hardware. So your oscilloscope is pretty useful. Logic analyzers, very useful, very, very useful, I should say. And then like your benched up power supplies and that kind of stuff. And then specialized hardware for the bus protocols that you're trying to analyze. If you can capture those, either to like a laptop or Raspberry Pi, whatever, then you can start to use tools to actually decode the data moving across it, and that helps a lot.
Yeah, like the bus pirate. I don't know if you've ever messed with that. It's like saved my life a million times. It's like, I know this is a serial protocol. I don't know. I'm not sure if it's SPI or I2C or what it is, but like you just pop this thing into a USB, pour it on your development station, and then, oh, there you go. There are all the bytes for the protocol. Like the tooling is getting better very slowly, but to your point, there's, these things get pretty complicated. And so the people that are engineering the systems tend to reuse the same protocols and microcontrollers and design principles because they work, right? And ultimately, the people that engineer these systems want to make them work. One of the interesting things that's starting to happen, though, because there's this cat and mouse game between people who engineer these systems and then people who reverse engineer these systems, is that we're actually starting to see more and more anti-tamper, anti-reverse engineering techniques on the OT side. These have been around for a while. On the IT side, you see things like anti-debugging, you see things like code obfuscation or encryption and code enclaves and cryptographic signing and all of this stuff that tries to get in the way of the person that's either reverse engineering or building undocumented features on top of the thing that they're studying. But when there's hardware involved, necessarily some of these things are going to be different in how you prevent reverse engineering. What are some of the things that we see today that make it harder to reverse engineer OT components?
So definitely on ECUs, ECMs, and these have been around, for a while, but we do see like a seed key algorithms where to communicate with an ECU, you have to kind of have like a matching sequence, and it can be hard to figure out if you don't have an actual reference system to observe. And I would say one of the harder things is not with an OT system, like you don't have a full train that you can just sit there and plug into. Usually you may have a component of a train. And then we also are seeing more, code signing, code verification, which was actually absent for a long time, but that's starting to come up more. And then what I anticipate seeing more now that it's really taken like the mobile market is trusted platform modules and secured boot all the way through, like, when something starts up to like loading the software from maybe an external EEPROM or an update process.
Yeah, we're starting to see encryption on some of the protocols, right? Like for older systems, doing basic encryption means a lot of computational overhead. And these systems typically have really, really tiny, like low compute capacity controllers on them. And so adding security on top may double or triple the computational demands. So historically, things like CAN buses and ARINC on aircraft and MIL standard 1553, like we haven't seen encryption most of the time, but we're starting to see a bit more of that, particularly with things like firmware updates, where you've got cryptographic checks that happen on the ECU before it'll load firmware into memory. Definitely makes it harder to attack these systems and also to reverse engineer them. And even some simple stuff like rubbing the model numbers off of chips can be like pretty irritating when you're trying to reverse something. Super annoying, right? Because when you have that model number, when you can go, you mentioned this before, you can get a what's called a data sheet, right? And the data sheet is a really, there's high variance of quality with data sheets, but data sheets will tell you a lot, especially in the case of a microcontroller, about exactly how that thing works. And sometimes if you don't have the model number, you'll have to like observe the thing and like put oscilloscopes on all the pins and say, oh, okay, I guess this is a GPIO pin. This one looks like it's SPI. This one looks like whatever. And you try to tease out if it's got a JTAG or whatever. And then you just use, to your point, educated guessing to say, okay, I'm pretty sure this is an STM family of microcontrollers. This is a PIC microcontroller or whatever. And then you just start looking through data sheets to look up the pinout matches.
And all while trying not to short pins and ruining your hardware.
Or to Brian's point, you buy 10 of them.
And sometimes you can do really interesting things to like leverage publicly available information. For example, in the United States, if you have something that emits an RF signature, you have to have it with the FCC. Oftentimes, you can actually get pictures and component breakdowns of the different pieces in those devices if they're truly FCC certified.
Because they have to file
it. And that can kind of shortcut what is normally a very consumer protective piece where like people knowing what they're getting, they know how it works. The government is certifying that this isn't going to give you like, some crazy cancer or something. But now the information is now out there for people to break it back down, figure out how the interior components work to manipulate it to do some other thing, right? So there's a lot of
Totally.
open source information that when amalgamated together can produce some really interesting like insights into what's going on a device.
Yeah, patents are another one, ironically, right? Like patents are there for IP protection, but I mean, you have to expose how the system works. And a lot of times in patent filings, you'll see really detailed sketches and schematics of like how these electronic components come together. And you can use those. They're just greatly accelerate your reverse engineering process. So, I mean, if I'm thinking about getting into reverse engineering and I hear this conversation, I'm like, okay, it sounds pretty hard. There's a lot of like terminology here. IT reverse engineering sounds interesting. I can like hack games. I can like get to know how Windows works and pull down malware and understand how all of these like really devastating crypto locker attacks happen or how people are building exploits. Like that seems really fun. And then you hear the three of us like telling war stories about how difficult it is to interact with hardware and add that on top of the reverse engineering process. But we do it anyway, right? Robert, what is the thing that like attracts you to OT and reverse engineering in this context, given that you've had a background in IT reverse engineering, but still somehow are attracted to pulling firmware off of microcontrollers rather than opening up an emulator?
I would say that even though I'm a computer cyber person, I really work with my hands, and I like being able to see my labor reflected in the physical world. I actually don't care that much for reverse engineering. Like, I'm gonna throw that out there as a senior reverser for Shift5. Sorry guys, but reverse engineering is always a means to an end.
Is that a edit signal?
And in this case, like, it's really cool to be able to see, like, you take something and being able to interact with it, having started knowing nothing about it, and then seeing that reflected in the physical world, like being able to make a electronic control module of some kind, like stop working when you really want it to. It feels pretty good. And then, one of the projects that we had for Shift5 was actually, reverse engineering a train protocol for interoperability, because, there's sometimes when these systems, they talk to each other, and the OEMs don't want to allow competitors to come in, and being able to go in and produce a product that was better by reverse engineering the diagnostics protocol, and then being able to get better information, better like fault monitoring, better alerting out of that. It actually felt really good.
Yeah, there's something really satisfying about going to these like really expensive multi-million-dollar assets that have digital components in them and apply principles that have been in the IT domain for a really long time, and then see like 50 or 100% improvements in productivity and the way that people are maintaining these things, because, we're able to get in there, understand these weird protocols like that very few people take the time to learn about, and layer functionality on top of it, as well as protect them from cyber attack. Because as I know you've seen, Robert and Brian, you and I have seen this a lot when we were in uniform. Like, these systems were just, a lot of these OT systems were never designed with cybersecurity in mind. They were designed for robustness in the physical world and like having different operating conditions where they would be able to fail over gracefully. But they were never designed with like a witting adversary, with a Robert, like, banging his head against the wall, trying to figure out how to make a cyber attack against an engine control unit. And having that witting adversary, that enemy that gets a vote and is trying to evade what you're doing, is a completely different ballgame than worrying about, a runaway train condition, for example, because the brakes are failing. Both really important, but it just turns out that historically, no one really thought about the cybersecurity of these things. And you can't really think about the cybersecurity of these things without having a grounding in reverse engineering, right? For all these points that we've talked about, you've got a finished artifact, and you've got to figure out where the flaws are on this thing. What's the protocol that it's speaking, so that you can monitor what's going over the bus, all that kind of stuff. So, Brian, where do you see OT security going? And do you think that reverse engineering will be an important skill set in where the OT industry is moving?
Well, it's kind of interesting if I have to give kind of an analogy about how an OT system works versus an IT system. You can think about an OT system a lot like a web API. in that something else is running some software that you can't really see, but you know if you inject certain input signals, certain stuff will come out. So if I send my encrypted message saying, yes, I have an Amazon account and I want to buy this pair of socks, then the output will be 2 days later, you have a pair of socks like on your front door, right? But you don't really know how the software works on the inside. And so I see in the IT space, a lot of people are reducing their reverse engineering risk by never putting the software in your hands. 5-10 years ago, everybody bought a copy of Word on a CD, and you had the no kidding binary that if you had the time and means, you could potentially reverse engineer out what it's doing. Now, Microsoft did a lot of work to make sure you couldn't do that, but it was possible. Nowadays, if your copy of Word actually resides on an Azure cloud somewhere in the Office 365 environment, so that you get permission to use the services, but you can't look at the code, that makes it much more difficult. Now, to me, what's interesting about the OT space is in some ways they're going the reverse direction. In that, 10 years ago or 20 years ago, a lot of the microcontrollers on major OT components did very simple jobs, right? Like, hey, my job is a digital engine controller. We're kind of exploring this whole compute space as an OT company. And all we're having you do is smooth out the acceleration curve on a car pedal by taking 2 data points, doing a calculation, aka just like doing the average value, and then outputting that as the actual output of someone pressing down on the pedal. So you don't get jerky responses, you get nice, smooth fuel flow to the engine, right? Kind of relatively simple things. Nowadays, as people are getting more and more enamored about like the cool stuff that embedded computers can do and how you can save fuel, or you can make cars faster, or you can spin satellites at a perfect amount of like consumption of solar energy, people like on the consumer side and on the design side are demanding more and more processing power on these OT components. So even nowadays, something like a tire pressure monitoring system on a truck, right? Before, you used to know when your tire was flat, when it was literally flat, you couldn't drive anywhere and you could hear the metal on the road, right? But now you have systems that are attached physically separate to each tire. They are communicating on RF waves using certain packet protocols to be received by an antenna. Then antenna is attached to your car that has a processor and memory running that allows you to say things like, oh, tire number 1 is at this pressure, it is low, and it has to process that raw RF input, then process it again to turn it into a message to send over the CAN line that connects all the components of the vehicle, so that it can pop up in your display saying like, hey, you need to go to the gas station and use the air machine to pump up your front left tire, right? So all of these like consumer desires are increasing the compute power that's available on these embedded components. And quite honestly, the engineers that are responsible for adding these features, they're focused on what is best for the maintainers and for the consumer to get for feature addition. They are typically not, these guys who've been thinking about cybersecurity problems for decades, right? And so often you'll find that what reversers find are flaws were meant to be features, right? Like, oh, I'm a maintainer, I have a special doodad. When I plug it in and connect this pin to this pin, I get it to just spill all its information about what the errors on the computer are, right? When in reality, if someone can figure that out by doing reverse engineering on it, now I can learn a lot or do a lot to a vehicle that's not meant to be messed with. And so I think as you go into the future, as you have all these different features being added, one, unless somebody sits on top and figures out a way to make one single protocol to rule them all, which in my practical experience has never happened, then there's going to be all these different kind of protocols running along the lines. And in some ways, people will assume that makes them more defensible, right? It's like, this is, our company's protocol. We make cars. We're the only ones that use this. We don't give out the documentation for this, so nobody's going to figure it out. When in reality, I think as the value of the hacks go up, if I can hack onto somebody's car and say, like, send me 0.1 Bitcoin or I'm going to crash you into the ditch, suddenly that becomes much more useful and a high payoff, especially as bigger things like oil, gas, shipping, planes become more and more literally controlled by embedded controllers, not even just talking about autopilot and the like, but how they detect where they are, where they're going through their transportation lanes, how they communicate with other devices, how industry is getting its data, and people automate more and have manual processes for less, then kind of the
the concern from the malicious attack perspective is higher because the payout is higher to somebody who wants to do something malicious. So like,
Right.
and the components themselves are getting more complex, and generally more complexity gives you a greater attack surface, and you only need to win once. That's
right.
The beauty that Rob and I have
Yep.
about being people with an offensive hacker mindset is the defender has to win every time. Right.
Or at least when they lose, they need to figure out that they've lost very quickly so they can kick you out of the system.
But the attacker only has to win once. And
Right.
so like if you can find that one win across a very large complex attack surface, and that's the way that embedded OT is going, then you're in the money. And so that's really our job, is to make sure that somebody's thinking that way, so we can point out those flaws in different vehicles or OT systems that we assess and say, hey, this is a flaw, a piece of your attack service is left open. Let us help you fix it. So that way you don't have people looking at your device in the same way.
Right. And I mean, we're already seeing attackers targeting OT heavy companies. It's just that it's pretty lowbrow stuff right now. I mean, we're going to talk about this next week on the podcast, the Omnitrax hack. So this is a freight operator, a locomotive rail operator who got hit with crypto locker malware that shut down a lot of their IT infrastructure. And that's just stopping them from kind of conducting operations because they're not able to access information. Imagine if instead the attackers were able to ground an entire fleet and hold the fleet hostage and just completely stop business operations. Like, that's not science fiction. We see this every day, that these systems are totally vulnerable to an attacker, like well-orchestrated attacker getting access to these systems and then burying themselves into it so that you're never going to find them and you got to pay some ransom for them to come off. Right. Mm-hmm. So I totally think, unfortunately, that's where we're headed. And we, the cybersecurity community, need to start building safety measures into these things so that doesn't happen. Robert, what are some things people that are interested in getting into reverse engineering can do to learn more about OT hacking and hardware hacking? And, are there resources out there, books they should be reading, talks they should be listening to on YouTube? How do you stay sharp?
I think a lot of the cybersecurity community is going lower level. I feel like a lot of the attack direction has been getting closer to hardware as the upper level software defenses get better. So Twitter is honestly people are sharing a lot of their original research on Twitter. It takes a little bit of curating your list to make sure that you're following people that are, putting out good work. Same thing with other just forums and communities on the internet. And then all the security conferences, keeping up with what people are doing. That's a great way to keep abreast of everything. And if you're looking to get started into it, honestly, my advice is do not start with hardware platforms. Start with something like, a Windows or Linux are great. Yeah. There's a lot of resources out there. I think everyone, at least where in my path up, we all got started doing crack me's.
Yep.
So you take a little piece of software and, figure out how that works, modify its behavior to bypass a fake registration screen, that kind of thing.
We just had our first episode of the podcast. Brian was on. We talked about CTFs, right? Mm-hmm. And there are all kinds of CTFs out there that involve reverse engineering and binary patching to do exactly what you're saying. Something that's supposed to be manageable, what to do in a few hours or a few days, and you can take your time with it. And there are solutions posted online. So I think that's really good advice. Maybe start with that and then get into trying to glitch firmware out of microcontrollers as a next step, right?
And learning your basic tools that translate. So, right. IDA Pro used to be hugely popular as a disassembler, and then with the Hexrace decompiler with it. But ever since the NSA, the National Security Agency, released Ghidra, it's free, it's excellent, and it's really lower the cost of entry into what I consider one of the most fundamental disassembler, decompiler functionality tools out there.
Awesome. Well, I think that's really good advice. Well, I know we're at the end of our time here. So Robert, Brian, thank you so much for taking the time out. This was a really great show, and I hope to have you on again soon.
All right. Thanks, Josh.
Bye. Thank you for listening to this episode of Planes, Trains, and Tanks. If you enjoyed this episode, please consider leaving us a review. To learn more about Shift5 and our products, visit our website at shift5.io or follow us on LinkedIn and Twitter.